So, I hope it records parallels. I'm sure it does. Alright. So, I am not going to go through the code I already wrote for this. We'll go through making this thing from scratch, right? So the first thing we're going to do is we're going to come up here, and so you guys are used to MPLAB 8. MPLAB X has a little bit more functionality, a little more information for you, a little easier to use interface, and it does a lot of stuff just automatically for you. So first thing we're going to do is we're going to say new project. If you do have an IDE 8 project, which you guys probably have a few now, obviously, since you're in digital, you can actually import it to the MPLAB X because they're still transitioning. They're still allowing you to download 8. They're not going to be for much longer. This is going to be their new flagship kind of thing. They're going to totally abandon 8, but for now you can actually implement if you want to. You can also do pre-built stuff, so like hex files. I don't know if you guys have gone over hex files in class, but hex files are basically the output of your file. Your MPLAB X, when it compiles something, it turns it into a hex file, and then it shoves that hex file into the chip. The hex file is what actually tells your chip what to do. It's like breaking it down to machine code. So you can actually take a hex file and just load it in there. Among other things, they have samples. That's kind of cool. So you can come in here later on and say, oh, I want to see, what is your PIC18 template, or I don't know. They also have a lot of example code, but we'll get into that later. So we're going to do a standalone project because we're just going to build something from scratch right now. The next thing it says is, what family are you part of? Well, the family we're going to be part of today is the PIC24 family. And then it says, so now what chip particularly are you using? So you come in here. The chip we're using today is the PIC24HJ. HJ, so FJ just means the standard model. HJ is the high speed model. FJs have a maximum speed of about 20 megahertz. Maximum instruction cycle 20 megahertz. So the clock cycle is 40 megahertz. The chip we're using has a clock cycle max of 80 megahertz. So we're using the PIC24HJ12GP201. You can also just type that in if you prefer. So we'll hit next. The debugger, the hardware tool we're using today is the PIC-Kit3, which you guys are used to. And then it's going to ask you what kind of compiler do you want to use. So I have a few compilers installed on this machine. You should only have the ASM30 is by default, I think. No, actually, you may not even have that. You should have definitely at least the XC16. That's the compiler we're going to use today. It is the C compiler for 16-bit microcontrollers. There's also XC8, and there's XC, I think they call it 32 or 30 or something like that. And those are for 8-bit and 32-bit microprocessors, respectively. So we're going to use XC16. The project name, we'll just call it Micromouse, even though this is not the Micromouse. And then make sure you save it somewhere where you want, and I'm going to put it in my Dropbox so I can give it to you guys later if you want it. No, it's not actually. And then you can set it as a main project. That just means whenever you open up MPLAB X next time, it will open this project. And then okay, so now once you have this made, the first thing you got to make, you go to the source files, you hit new, and the first thing we got to make is a C main file. This is our main file for all the Micromouse. This is where it starts, where it looks at all its initial information, and you can build off of this. Make sure you choose the folder for it as the folder that you're in, which is, in our case, this is the Micromouse project file. The Mac side, it was giving me, it was wanting to put it in different folders. I don't know why. Header files. So, okay, it comes, default with your include, standard I/O, and standard libraries. That's pretty default. Everybody uses those for the most part. That's the normal C stuff you're used to using every day when you program something in C. But we want to include two additional files. First of all, we want to include the P24HJ. I said P24, not PIC24. I don't know why they decided to make that convention, but they did. The 201.h. This gives us the header file for our specific chip. That header file is important because it tells our compiler, our code, where everything is in the chip. Because every chip is different, the pinouts are different, the register locations are different, the program memory locations are different, the data memory locations are different. So like whenever you go and you buy a chip, it'll have a lot of information, like how much data can you put in here, how much data memory does it have, how much program memory does it have, how much RAM does it have. Well, those have different amounts, so their address locations start at different areas. So this is one of the things that tells you how to do it. It also is important to you because it also does, and I don't know how to do this on the Windows side. We'll open it in a second here. But it also has your configuration bits, which are the bits that you need to make this thing run. The second include file that we want to make sure we have is going to be called libpic30.h. And the only reason we really want this, that that I'm crazy about this header file, is it has three really cool functions in it. So we can come over here now. We've included these files. Now, I don't know if you guys remember from C, but you notice I use these brackets here, right? These brackets mean go to your default searching areas, right? MPLab already knows to look in its default areas, which we're going to go grab these files from just to look at them. If you put quotations marks, it will also look in the directories that you tell it to, which would be like its own directory. So if you put quotations marks, it would look wherever it exists. You could put header files in there, and it'll include those. So it would look like that. It would have quotation marks like that instead. But since we're going to go to the default location, which is where MPLab installs everything, we're going to do that one. So now we add existing items. Well, let's get out of everything so I can show you guys. So is anyone here on Mac? Okay, you're on Mac, Simon. So are you doing the Mac MPLab? Okay, cool. That's fine. So if you're on Mac, you're going to go to Applications, and you're going to go to Microchip. And if you're on Windows, you're going to go to Program Files, and you're going to go to Microchip. Once you get in there, everything else is the same between Mac and Windows. So XC16, that's the compiler we're using. I have 2 versions downloaded because I had one installed in the past, and then I downloaded the new one today. So gosh, oh my God. We're going to go into 1.2, and so the files we're looking for are going to be under support and under PIC24H. So we want the header file, first of all, so we can check that out. And that is right here. So we can include that. Now, just to peek in here, just to see what's going on. So sometimes it'll do this, and that's really annoying. You have to save your project so that it knows that you're including this file, because it will flip out on you. It's like very finicky. All this Microchip stuff, it's just a little bit finicky. They're really awesome because they do a lot of good supporting documents. Thank you. So she has to go to work. She's like running late for work. Sorry. So there's a lot of good supporting documents, but sometimes they have little stupid things like this. So that include file has to be in your main file, and your main file has to be saved and updated for this header file to recognize that, because it saves a certain little processor setting in the project file that tells it, hey, I'm using this processor. So once you do that, now you see everything's cool. It's happy with everything. Now you come out here, so you can see right here off the bat, they're calling out, we're defining working registers and things like that. By the way, the PIC24 family, you guys are used to 1 working register. There's 16 on this family, so they have a lot of working registers. But as you go down, you'll see there's a whole lot of other stuff. You've got, it's basically telling itself, it's telling the compiler, hey, this is where everything is. Here's how you interact with everything. It's defining stuff for us so that we're not, we don't have to access things by address. We can actually just call them by a name, so it defines it all for us. But the important part is, if we come down here, we'll see. So here's the interrupt service routines. Let's keep going down. These are a lot of the registers that are in this chip. Here we go. These are your configuration bits. And the first thing you'll see here, so these are really important. These are, as a friend of mine used to call them, words of power. The machine will not work unless you do these configuration bits. You don't have to necessarily set them all. They have default settings, but you have to make sure that the ones you're using are put in the proper place or it will not function. So this first one we have here, you can, and this is great because they do a great job of kind of labeling out, telling you here's what's going on, and even here's how to use it. But you have this first one. It's called FBS. This is the configuration bits for the boot segment. And so the boot segment has two options here. It has the write protect and the flash code protection. This would be a little more important to, say, a big company who's programming chips and they don't want people to be able to overwrite their chips or something like that. That's what that information is for. We don't need it. But if we come back down here, we see, okay, this next one, this one has the general segment code. Do you want to write protect the general segment code? No, we don't really care about that. Here's what we do care about. We're about to do analog to digital sampling. We want to configure the clock of this chip to be as fast as possible. Why? Because why not? I mean, you can have a slower chip if you want, if you don't need fast. But most of the time, what I do off the bat is just go ahead and configure it to be as fast as possible, just so I can fully utilize the chip if I want to. Unless you have energy concerns. Energy concerns, you might want to lower the speed of the chip so it's not consuming as much energy. But the first thing here you see is F oscillator select. This is the oscillator selection configuration bits. And so the way we're going to use it is we're going to have underscore F oscillator select, and we have an open parentheses, and we put all the options, and we bitwise AND them. So what does that tell us? I mean, that tells us that the options are probably a lot of Fs, right? Which means that we have a lot of ones, and we keep ANDing them with more ones, and we zero out only the things we don't want, or that we would have a configuration bit to set. So here are the options. You have, and you'll notice if you look here, you'll see a lot of the times you can see it's just one bit at a time. Only one bit is getting set, or is getting cleared actually in this case, versus everything else. And that's how it looks at it. So it's looking bit by bit. It sees, is this bit set? They want this option. Anyways, so the first thing we see here is F oscillator select. We'll come back in here, and we'll put it under our include files with F oscillator select, and we want to make sure we get, okay, oscillator mode. What do we want? We want, there's internal fast RC oscillator. There's internal fast RC oscillator with the PLL. There's using a primary oscillator, which is a XT and HS and EC, or if you want to add a PLL to that. There's a secondary oscillator, a low power oscillator, and then two internal fast RC oscillators with divisions that you specify. So we want the internal fast oscillator with PLL. That gives us a phase lock loop which we can alter the speed of the chip with. If you didn't use the PLL, then you would just have the RC oscillator. Its default setting is 7.37 megahertz. So we want to up that to, 40 megahertz. So we're going to want the PLL to do those changes. So we want to just go ahead and copy this name. We don't even have to type it ourselves. We'll say that name. Okay. And there's something else we want to set, right? Internal, external switchover mode. Do we want to start up the device with the user selected oscillator source, or do we want to start up the device with the fast RC oscillator and then automatically switch to the user selected? So this may be useful if we're using something like a crystal oscillator and we want to make sure we get started up and everything is configured first before we set up the other oscillator to take over our clock. Maybe it takes time to start up. Maybe, I don't know, maybe the chip itself triggers it. I don't know. But there could be some reason that you want to make sure it gets started up with the fast RC oscillator and then go. But for us, we just want to go ahead and start up, say off, and say, just keep using what we're using. So just use our oscillator selected choice. And go ahead and copy that name. Come over, put that there. And there we go. The next thing we're concerned about, there's a lot of configuration bits in here, but we're only concerned about really these two. The second one says oscillator, what is it? Oscillator, it's just oscillator settings. I can't remember the exact name of it. Oscillator something. So it says, first of all, do you want to use, for the primary oscillator source, do you want to use the EC, the XT, or the HS? We don't care about that because we didn't choose that primary oscillator source. Then it says for the OSC2 pin function, do you want it to have digital I/O or clock out function? Well, we want digital I/O, right? We don't want one of our digital I/O pins to accidentally get set up to do clock output. So we want to make sure that gets fixed. F oscillator, and a lot of these are already defaulted to correct, but if you see something like that when you're changing these settings and you want to make sure it gets set the proper way, you can do this. And then the other one is, and we don't care about that. We just wanted to make sure that was set up as digital I/O. Okay, So that's it. That's the only configuration bits we care about. So we can go ahead and close this header file now. Now let's go back to these header files and add one more. This is the other one I was talking about a minute ago. This one's not in the PIC24H. This one's in generic. Oh my gosh, why are you doing this? Okay. We want the libpic30, right? And I just want to point out what I like about this one. It's got these functions called delay 32 and delay ms and delay us. This libpic30, if you define a frequency, so this is the first thing you want to look at, it says if the frequency is defined, or if it's not defined, we'll use this. If it is defined, if it isn't defined, we're going to set a default, act like this chip is running at 10 megahertz. So we need to make sure we define this frequency, which we'll go back and do in a second here. But what it lets you do is it will do the math for you. If you want to do a delay for 1 millisecond, it'll say, okay, well, I know the frequency of your chip, so I'm going to do the math for you and delay that long. And then also for delay 32 is delay this many clock cycles. And that's kind of cool. So you can just flat out say delay 7 clock cycles if you want to do the math yourself. But the nice thing is that you don't have to sit there and, I don't remember how you guys did it in digital, but a lot of times the people learn just, oh, make an I and then count up to some number and time it, and then you can try to use that as a delay. You know what I mean? So you're tricking it into counting. Well, this thing sets it up and says, I'm going to no op for exactly the amount of time you say. So it's very useful in that sense. So I guess the next thing is, how do we get that frequency, right? I'll send you guys this Excel file. I have a good friend named George Burrows who set up this really awesome Excel file that does the math for you, and I'll show you what I mean. Let me actually show you the data sheet first. So when you're using these microcontrollers, you want to make sure you have, you want to make sure you have the chip's data sheet in front of you, plus any family reference manuals that pertain to what you're going to be doing. So we'll want the ADC, we'll want interrupts, and we'll want input-output ports. So if we come back to the chip, everything is so freaking big. And we're talking about, what did I just say again? Oh yeah, so if we go to this chip, we'll see in the table of contents, which is right here, we look up the oscillator configuration. We go to page 87. Okay, so in this oscillator configuration, you'll see that there's an onboard PLL. And here is the block diagram for it. This block diagram describes what's happening to the clock as you configure it. So first of all, it takes the source or the external clock or the internal RC. Well, how fast is the internal RC? I already told you guys, but if you look up here, they'll say when they describe it, they'll say the fast RC internal oscillator. So I'm reading this to you because this is kind of one of the things you have to learn to do when you're programming microcontrollers, is read these paragraphs. It's actually kind of really useful. They say things pretty easily. They speak pretty good English to you instead of all this technical jargon. But besides that, they put a lot of useful information in these paragraphs. And sometimes you'll find information in these paragraphs that you can't find anywhere else. And they will be key to making your project work. So make sure whenever you do get to these sections and you're like, okay, I want to configure my oscillator, right? I want to go in here and I want to make sure I read anything that might pertain to what I'm doing. So the first thing it says here is that it runs at a nominal frequency of 7.37 megahertz. Okay, so this says take that internal RC, which we know now is 7.37 megahertz, and then we're going to do this phase lock loop pre-division. And you can divide by anything between 2 and 33, and then it comes out here, and this says right here, this frequency range must be satisfied at all times. So as soon as it leaves the PLL pre, it needs to be between 0.8 and 8 megahertz. So that's kind of key. you know, if you take 7.37 megahertz and you multiply it by 33, that's way more than 8 megahertz. And so you're going to have a problem with your chip. It's not going to work. The next thing is it says, okay, now that goes in here, and then it goes to the voltage controlled oscillator, which then has a PLL divisor that multiplies by somewhere between 2 and 513. I say multiplies, it's a dividing of a dividing. And so that's, they say M divide, but it's divide of divide. And so you get this multiplication. Here's the actual formula up here. So we have N1, M, and N2. This is how they look in the formula. But you can't just plug in numbers for the formula because you have to satisfy this, this, and this. So when it goes to the voltage controlled oscillator, it gets multiplied by 2 to 513. So, oh, by the way, just to step back for a second, I said multiply over here, but it divides, right? So you have 7.37, it divides. So you got to really worry about getting under 0.8, not over 8. But going back to this M, so it'll now take it and it'll multiply by 2 to 513. And after it leaves there, it needs to be between 100 and 200 megahertz. And then finally, there's a PLL post divider, and that'll divide by either 2, 4, or 8. So that's kind of another thing that's interesting. This is 2 to 33. This is 2 to 513. This can be 2, 4, or 8. 3 different numbers. It can't be anything between those. And then when it leaves there, obviously it has to be between 12.5 and 80 megahertz. That's the oscillator frequency. And then if you remember FCY, that's your cycle frequency. In other words, instruction cycle frequency. That's your oscillator frequency divided by 2. So if you have 80 megahertz, you have 40 MIPS, which is 40 million instructions per second. Okay? So there's your PLL loop. Now, what's the cool thing is my friend has a really neat calculator that he put together. It's an Excel file. And this calculator literally just, you can plug in values and you can test and see if they're working. So I can come in here and say, oh, I have 7.37 to start with, right? I can stick in 5. As long as everything's green here, I'm kosher. It works. And he put the output of F oscillator and FCY. So you can actually come in here and play around. You know, this one has to be 2, 4, or 8, so we can mess with this. Then we can come in here and say, oh, now we want to change this to 250. And you can see now I left these ranges, right? So that one earlier said I had to be between, like, I don't remember, like 15 and 200 or something. Now I'm at 368. That doesn't work. So now maybe I have to increase this to 12. Oh, and now I got these in the right range, but this went under. So you can mess around with it for a while. I'm just going to open up and look at what I did for my code just because I got one that's pretty close. So I did 3, 65, and 2. So we'll go back and plug those in to see that. So 3, 65, and 2. And what we get out of that, we get an oscillator frequency of nearly 80 megahertz, and we get nearly 40 MIPS of instructions, right? So, and you can see this is right on the edge, right? So I can't really mess with this a whole lot, but it's pretty close. Now you can get it even closer if you want to. There's an oscillator tuning register. We're not going to go into that today, but you can take that register and you can slightly tune it. It's put in there actually to compensate for temperature and moisture in the environment you put it in. So if you wanted 7.37, you might need to tune it a little closer to 7.37 or something like that, because those things are affected whenever you're in those environments. But you can also use it to your advantage if you want to get to an exact number for whatever reason. So I don't give a crap. This is close enough, and we're not going to go into all that, but yeah. Okay, so now we've talked about that. So once we get our frequency, we want to come back up here. We talked about how it needed to be defined, right? So we're going to make sure all our definitions are before our include files because we want to make sure they get defined beforehand. So we want to define our FCY to this number, which is 3992. Let's go back. It's going to take a second. 3992 083333. Whoops. 083333. So that's 1 2 3 1 2 3 1 2 3. That's good. And so then we're going to make it UL. That means unsigned long. Since that number is really big, it doesn't fit in a regular register, so we want to make sure it's an unsigned long register. So we define that, and now our LibPic30 will know what our frequency is, and we'll be able to use those delay functions if we so please to. Okay, so now we have our frequency defined, we have our configuration bits set up, but how do we make sure we get that frequency? Well, we need to configure the clock. So let's make a new function. We'll call it config clock. We don't need to pass anything in, right? Because we're just configuring a clock. Alright, so this config clock, what we're going to do is we're just going to set up the PLL pre, the PLL post. Let's just say 0 for now so that I can show you guys this. And the PLL, actually let's do that in order so that we don't mess that up. It's PLL div. Now, let's go back to this guy right here. There are the PLL pre, the PLL post, and the PLL div registers right here. There's also, in this oscillator configuration, you can see up here, let's not worry about that right now. So for the PLL pre, post, and the divisor, you'll see when you look at here, it says for PLL post, 0, it means 2. 1 means 4, and that's the default, and then 3 means 8. So we have 0, 1, or 3. 2 has been reserved, so we can't use that number. I mean, it's just not, that bit is reserved. Or that bit configuration is reserved. So they're looking at these first 3 bits here, and so we have or these first 2 bits, sorry, which can give us only those configurations. So we said back in that Excel file that our PLL post is going to be 2, right? So we're looking at PLL post. So we want to make sure PLL post is equal to 0, which we did do that. So that's already set up. We come back in here, the PLL pre, this one says 0 is 2, and then I believe this is the 35, so I think it's all minus 2, right? Is that what it is, minus 2? I thought they had the math on here.
Yeah, I thought they did.
It might be the family reference manual. Okay, scroll no longer works. There we go. Was it? No, that was just an example. Well, okay, so the point is to watch out for is this one actually, you can see here that 0 is 2, 1 is 3. So if you want 3, subtract 2, you have 1, right? So if we come back in here to the pre, you see we want 3, so we'll subtract 2. We want the register equal to 1. And then if we come back in here, we'll see the PLL div. And this one is the same way, I believe. Yeah, it's 2 is 0, 3 is 1, 4 is 2. So we just take the number we want, subtract 2, and that gives us what our register should be equal to. So we have 65 here. We're going to go back in and say 63. Okay? So now we've configured our clock. We need to make sure that gets called whenever our main function is run. So config clock, probably one of the first things we want to do. And that's that. Now that makes sure our chip is running fast. So what next? Now we have our clock. We have our frequency set up. We have our include files. We have our configuration bits. So the next thing we want to do, let's go ahead and configure the pins. Before we go into ADC stuff, let's configure our pins. So we're going to say void config config pins. And, oh, I need to put a void in here. And we'll come in here. Now, to configure the pins, we need to go look back at our data sheet. Find our table of contents. Find our IL ports. We want to go to page. It wasn't letting me. I can click in the index. I just can't click on this. I don't know why. So we want to go to the I/O ports. That's page 101. Actually, I could probably do this. There we go. And so we'll read this. Okay, so I/O ports. This says all port pins have 3 registers directly associated with their operation in digital I/O. The tris register determines whether the input or the pin is an input or an output. If data direction bit is 1, it's an input. All port pins are defined as inputs after reset. Reads from the latch, read the latch. Writes to the latch, write the latch. Reads from the port, writes to the port, writes to the latch. So the latch is really your output, and the port is your input. So you guys have been using GPIO, right? And so you don't have input or output necessarily defined. But since these pins on this chip have analog sampling, they have a tri-state setup. So what that means is that there's 3 states it can be in. It can be an input, it can be an output, or it can be a high impedance. And the high impedance is used in order to detect analog voltage. So in our case, we want to make sure we set the tris bit, and then we also want to make sure that it's not an analog pin. Now, in this particular case, I've chosen a chip, and let's look at this chip's layout. I've chosen a chip that's 18 pins. I'm using 3 digital outputs, and they're hooked up to LEDs right here. And I'm using 1 analog input that's hooked up to a potentiometer so that I can just cycle through 0 and 3.3. So in this case, on this specific time, I'm able to just use analog pin number 2, or it's analog 0 on pin number 2, and I'm using the digital outputs RB9, RB8, RB7, which do not have analog capabilities. So I actually don't need to make sure the analog is off. However, that was pretty dramatic. However, if I were to use a pin that had analog capabilities, we'll have to make sure the PCFGL is cleared. And this says it right here. So the 81 PCFG and the tris registers control the operation of analog to digital port pins. The port pins are desired. The analog inputs must have their corresponding tris bits set. If the tris bit is cleared, the digital output will be converted. The 81 PCFGL register has a default value of 0. Therefore, all pins that share analog function are analog, parentheses, not digital by default. So this is one of the problems that a lot of people that get into microcontrollers when they're first setting up their I/O ports encounter, myself included, is that if you do not change that pin to a digital pin, it will not work. So a lot of times you want to use digital because digital doesn't require any setup, really. I mean, you just have to make sure the tris is set up, and then you start writing to the latch, right? But if it's not if this PCFG is not set for that pin, then it will not work as a digital pin. It will only work as analog. If they're configured as digital inputs, obviously, it will not convert analog input. So you can't have both. So the PCFG register literally just has bits. And we'll go to the register map. Let's look at the register map. Where is the register map? I can't remember where the register map is. Here it is. In there? Well, there is a PCFGL register and a PCFGH register. It's low and high, and it has to do with the number of pins that you have. If you have a lot of pins, you'll use both of them. Typically, you only use the PCFGL, and I thought it was on here. This is one of those things that I talked about that's in a paragraph. So you notice we read that all in a paragraph, and it's not really anywhere else. So this is one of those things that can really mess you up if you're not paying attention to it. But its bits correspond to the analog pins. So if you wanted to make sure that PCFG8 was 1, it would make sure Was it PCFG8? Let's see. I have another file where I use that. It's always good to make sure you keep all your projects pretty well organized so you can always refer back to them later, because there's going to be times where you don't remember exactly how something worked and it takes you a while to figure out otherwise. There we go. Yeah, PCFG6 and 7. Okay, so it doesn't exist on that chip where I was saying, but if you look back in here and you say, okay, PCFG6, it will go to that spot and you can set that bit. It corresponds directly to analog. So PCFG6 is for analog, AN6, whichever pin has AN6. So we don't have to do that though. We just have to make sure our tris bits are set. So I said we have 9, 8, and 7, right? So tris B9. I say tris B9 because it was RB9. Tris B9, we want to make sure it's output, right? So we want that set to 0. And then as soon as we do that, we want to say latch B9 is equal to 0 just to make sure it's off when we're configuring it. Now, sometimes it's annoying to remember this kind of stuff, right? Latch B9. So instead of calling it latch B9, we can come back up here in the definitions, and I'm pretty sure most of you are pretty familiar with this, but just in case, you can come up here and say underscore lat B9. We're going to define it as, let's say, H LED. So that's our high LED, right? And then let's go ahead and pound define lat B6, or sorry, lat B8 as M LED, medium LED, and pound define lat B7 as low LED. So we're going to do, oh, and I should probably show you guys what this is. I wanted to show you guys off the bat. I guess let's take a quick break on that to show what does this chip do. So I'm powering this chip from the PIC kit because I don't want to hook up power. And you can do that, oh, I should show you guys that. If you right click your project, go down to properties, and you click the PIC kit, and you say open categories, we want to go to power, you can say power target from PIC kit 3. And you can set the voltage level for that. You can go anywhere between 3 and 5 volts with certain increments. Say OK, and then your project will now be powered by the PIC kit. So, cool. Need like a screwdriver or something. You got a screwdriver?
Yes. You just did? Yeah.
Alright, so you guys can see on this board as I increase the voltage, hopefully it's being powered right now. No, it's not being powered right now. What's going on?
You should probably start with.
That's a brilliant idea.
Is it plugged in?
I might have to reprogram it. So I guess we'll just hold on until we finish this. Anyways, the point is, what it's doing is it's sampling the analog channel, and it'll light up based on the voltage. It's checking, is it higher than 1 volt? Light this one up. Higher than 2 volts? Light 2 of them up. Higher than 3 volts? Light 3 of them up. Simple setup just to show that we're doing analog sampling. Okay. So we've defined these names for it to make it a little easier to work with. So we can come back down in here. We can say this is HLED. And let's make sure that's 0, right? That's what I called it, right? Oops, I did it the wrong way. Jay, you're the software engineer. You should have called me out.
I wasn't paying attention either. I probably would have done something.
So next thing is make sure the tris B8 is equal to 0. So we have an output I always remember that as the 0 looks like an O, which is output, and the 1 looks like an I, input. So MLED equals 0, and then tris B7 equals 0. LED is equal to 0. Okay, so now we've configured our digital output pins. The next thing we got to do is our ADC. So void config ADC. Okay, so here's where all the fun stuff starts. Yeah, okay, you hate everything. So we want to do ADC configuration. Let's go to our table of contents. All right. So some of these configurations, some of these peripherals are really cool because they'll give you right off the bat. They'll say to configure the ADC module, select the port pins as analog pins. So that's that 80 PCFG whatever stuff I just showed you guys. Then it says select the voltage reference on the source to match the expected range on the analog inputs. So that's something that's interesting because you can have different types of references. So these chips, their pins can take no more. Some pins can take up to 5 volts. But everything else is rated to 3.3 volts. But let's say you wanted to check between 0 and 1 volt. You could give it a reference of 1 volt, and you can use all of your data between 0 and 1 volt. It's really important because when you talk about sampling, and I should write this on the board. Where is a marker? There. So when you talk about sampling analog voltage, the way it works is it goes in and it's called a sample and hold process. So it takes some voltage, it goes and gets filled up on a capacitor. That capacitor holds that voltage, and then it reads it and says, okay, now I'm going to turn that voltage between these two reference points into a numerical value. So let's say we're working between 0 and 10. Let's say let's forget about bits. Let's say we have 10 numbers, or I guess that's 11 numbers, huh? So let's say 0 and 9. We have 10 numbers to describe what is the voltage, right? So let's say we are going to use reference voltage of 10 volts, and we're going to use reference ground of 0 volts. And our signal reads everything between 0 and 1, right? So it comes back and it's like 0.5 volts. Well, we've said that 0 is equal to 0 volts. And we've said that our top reference is equal to 10 volts. So that means that if we want to do 0.5 volts, or let's just say 0, 1, 2, 3, 4, ... and it goes all the way up to 10 volts, right? So we can take 10 volts, we can divide it through, we can say this is 0, let's just change it back to 10, that makes it easier actually. This is 0, this is 1 volt, this is 2 volts, this is 3 volts. Well, let's make this 0.51. What does it say it is? It says the closest thing to it. It says it's a 1. What if we make it 0.76 volts? What's it say it is? Oh, it's still a 1. What if we make it 1.4 volts? What is it? Still a 1. So we want to make sure that range is as close to our minimum and maximum as possible so we can look at those values and say, it's here, it's there, we have this huge range, right? So now let's do the same thing. But let's say this is 1 volt. Now we have 9, 8, oh, 2, 3, 4. There's some stuff between it. Now this is 0.1 volts. Now this is 0.2 volts. Now this is 0.3 volts, and so on. So now we set our signals between 0 and 1 volts, right? So let's say we get 0.34 volts. What's it tell us? It tells us it's 3. Well, if it's 0.36 volts, it tells us it's 4, right? So one thing that's important to look at here is that, first of all, digital conversion is always going to be rounding. It's never going to be perfect. It's never going to exactly tell you what you're putting in it. Maybe sometimes it'll get lucky, But most of the time, it's not. It's going to be some rounding. But it makes it something that we can use. It it discretizes the system. It makes it something that we can interact with, because if we were to look at every value between 0 and 1 volt, guess what it is? Infinity. There's infinity possibilities, right? It could be an infinite number of voltages. So we can't deal with that. Microcontroller can't say, we can't tell it, hey, there's infinite things, go. It's going to go, what? I can only do like 12. So in our case, we're using 12-bit sampling, so it can be between 0 and 4096. So we have a lot more precision than 0 to 10, but it is nonetheless a finite number that we have to work with. So let's go back over here. We say, okay, so now we just learned about references. We know there's some deal that's going on with references. Then we have analog conversion clock to desired data clock, right, with the processor clock. Okay, so what this says is how fast do you want to do analog conversions. So what are conversions? The conversions are actually taking that analog value and converting it to digital. So it's not the sample time, and it's not the time that it takes for you to, get your value or whatever. It's the time it spends converting it from an analog value to a digital one. The next thing says determine how many sample and hold channels will be used. So in this chip, we can do up to 4 sample and hold channels, and then we can do this little like ping pong type deal where you do 4 of one type and then 4 of another type. You can alternate them. It's called alternate sampling. And so we can actually sample up to 8 channels on this little bitty chip, which is pretty awesome to be 100% honest with you. I think there's only actually 6 channels or something like that, so you can only do 6 technically, but still, nonetheless, really cool. For our purposes today, we'll only do 1, but it's still interesting that you can do that many. Select the appropriate sample conversion sequence. So that talks about what, we'll get into that one in a second. That's a little more complicated. And then it says select the way the conversion results are presented. We'll do that in a second, talk about, and then configure the ADC interrupt if required. So it says if required there. So that's something to think about as well. We can use interrupts, which we are today, because interrupts are so important, and I want to just make sure you guys understand them because they are everything to a microcontroller. That's the whole purpose of these things, is to use them to interrupt, to do things as needed, rather than do things in a sequence. So that's the purpose of an interrupt. Like we don't want to spend power, time, energy calculating something we don't need to calculate. So the purpose of the interrupt is only bother me when I need to deal with something, which is just everything. And so Micromouse, that's like the utmost importance, because you guys are going to be pushing the processor to its limits. When we did our senior design on it, we had an ARM processor that was like 160 megahertz, and we were pushing that thing to the max. And we were having times where we were like, okay, we need to take this off because it's taking too long to get to this value. So you guys are going to be pushing this processor to its limits. It's not going to be like class where it's like this processor's job is to do something that a capacitor could do. You know what I mean? So just something to consider. All right, so this is the actual block diagram. So we talked about the sample hold thing, right? So you get this. These are the multiplexers that decide what pin you're looking at, what channel you're on. These are the channels: channel 0, channel 1, channel 2. So those multiplexers, those are set by your bits that you're going to choose for configuring this ADC, and then that value will be, when you have a sample, this latch closes, so it samples. That latch stays closed for the sample time. So you can change that sample time. We'll go over that in a second, but you can change how long you're sampling. So some things you want a long time, some things you want really short. But you got to consider that it's filling up a cap, and that cap's going to deliver this value. So that cap is kind of like a low-pass filter, so it's going to kind of ignore some of the noise for you, but it's also going to hold the value so that it has time to deal with it. But that sampling is interesting. That sample time is interesting. So one of the things you guys might be considering sample time for is your IR sensors. IR sensors send out a beam of IR, and that bounces back, and you have this IR sensor that says, what's the magnitude of this beam of IR. How long you look at it is very important. It changes everything, because you're going to need to do some math with that and figure out how long does it take, because we think of light as instant, and it's not. You know, it takes time for it to get to the wall and to bounce back. And it's infrared. So you have to sit there and say, how long is that going to take? And then how long do I need to look at it before taking that sample to get a good, accurate measurement of distance and not receive distortion from other IR sensors, because they're going to be firing off pretty quickly, right? So you don't want them overlapping and getting other distortion. So that's interesting. You got to be thinking about that. So this shows just the multiple chips. Here in this, we'll get down to this in a second, but this chip can use either the ADC internal RC clock, and it says, see the ADC electrical characteristics for the exact RC clock value. I really wish they wouldn't say this. It's so stupid, because you're going to go to the end of the book, or end of this data sheet, and you're going to find a number that they could have literally just put in number 2 for you. But you know, I guess it's good practice to get used to running around this data sheet, because this is going to be like your Bible while you're working on the Micromouse. You're going to have to go through this thing just constantly referring to different points of it. The other thing you can use is the internal oscillator of the chip. So you can use the chip's clock, or the ADC has its own internal RC clock. Well, what's the speed of that? Well, let's go find out. It says check the electrical characteristics, right? So come down here to electrical characteristics, and we got to see where is that ADC. It's bunch of stuff, bunch of stuff, bunch of stuff. Keep scrolling through. Some flash memory, some other stuff. What is this? External clock, internal RC, I/O timing. Timer 1, 2, and 3. All kinds of fun information here. This is seriously, this stuff is very useful. At some point you may be referring to it. So this is one thing that this company does very well, is document. Document, document, document. They have so much information out there. SPI, I squared C, ADC. So we're looking at the ADC, we see, okay, here's some of this characteristics: input voltage range, recommended impedance, alright, ADC internal RC oscillator period. So it actually gives it to you in period, which is 250 nanoseconds, which I guess we can throw into the calculator just to see. So 250 nanoseconds, that's milli, micro, 250, and we want to inverse that. So it looks like it's about 4 megahertz. That's pretty fast. I'm good with that. But we could, if we wanted to, have some variation of our clock frequency. Son of a gun. Alright. Let's go back to ADC. What page was that? 150 something. Here we go. Alright, now let's go ahead and start configuring. Now, when you get this ADC1 or 81CON1, this is our ADC1 control register. This is the first register we're going to use to configure our chip. So, what I like to do is I like to come in here and comment, make sure we know we're doing AD1CON1 register, right? Because I don't like to use long term, and I'll show you both ways in a second here. First thing is AD on. Is it on or is it off? Well, we want it on, but let's go ahead and turn it off while we're configuring it, just to make sure it doesn't do anything stupid. Sometimes we'll go ahead and turn it back on so we don't forget and just put it down at the bottom. We'll do that last. But sometimes these chips just act a little funky, and I can't really describe it. I don't know. It's kind of hard to put into words to describe what they do, but sometimes they just act a little funky when you don't take precaution steps. So just to take precaution, we're going to make sure it's off before we do anything with it. Now, I wrote _AD on, and that's because Microchip did this wonderful tons of work to put in those header files all the names of the bits of their registers. Okay, so like other companies, you go pick up a TI chip, you may not get this. They may tell you bit 15 is, can be these two things, which means that you'll have to call this register, and you'll have to literally do bit setting. You have to set all their bits or clear their bits. Microchip was like, hey, let's make it easier on them. We'll make AD on a unique name for the entire microcontroller, and the only thing it refers to is this bit. One single flippin' bit. And so they did that for every single set of bits or bits. So some of these are a set of bits, right? This is 2 bits. Form here, it's 1:0, which means there's 2 bits here. It's bits 8 and 9. So some of them are 2 bits, but regardless, they took the time to go through here and say, here's names for every bit. So I did underscore AD on. The other way you can call it, though, is this is the 81 con1 register. So we can come back in here. We can say 81 con1 bits.AD on. And that equals 0. So we did the exact same thing there, except for we did it by calling the register and then saying inside of this register we want this bit. Matt likes to use these bits here, like this, because it makes sure you know what register you're on. I just do this because it's shorthand notation, and it's it gets easier when you're writing a lot of configuration stuff. And then I just put over the comments what register I'm in. So it doesn't matter which way you use it; they're both great ways of using it. But yeah. So the next thing it says, next bit we got to worry about. Okay, so bit 14, unimplemented, red is 0. Something interesting to think about too. They show, before you even start trying to configure these bits, they show up here on these tables. Here's all our bits, and these dashes next to them, they show what their default values are. So this is, and they also show what you can do with them. So this is a read-write bit, which means we can read from it or we can write to it, and its default value is 0. So it actually starts off, right? So we made sure it was off by setting it to 0 again, which wasn't necessary again, like I say, but it's just better to do that. Some of these, U is unimplemented, so that bit doesn't even, they don't even care. I mean, it doesn't, I don't know if it'll let you write to it, but it doesn't make any change to your chip. Some of these are just read bits. So this is a read bit. I don't remember what the C stands for. Where is it? I think it means something like the software clears it. Then there's hardware clear, and then there's hardware set. So this is actually saying the hardware uses this bit. This is a done bit. And actually, this is for if you weren't using interrupts, you could actually sample this bit, poll this bit, and say, is the ADC done sampling? And when it is done, that bit will set, and then you can move forward from there. So you can actually read that bit. It's useful for reading if you're not using interrupts. But the hardware actually will mess around with that bit. So that's why they say HSHC here. So next thing is the stop and idle mode bit. This is the next one we want to deal with. This says, if we set it to 1, discontinue the module operation when it's in idle mode. If it's 0, continue the operation. To us, it really doesn't matter. I'm going to go ahead and ignore it because it's already set up to do continue operation in idle mode, and that's what I would prefer from it. But the other thing is we're never going to go to idle mode. I'm not going to program to idle mode today. Now, you might use idle mode in other future projects. Micromouse, sure as shit, is never going to go to idle mode because that would be like a bullet to the head. But if you had another type of chip, so like, for instance, Simon's senior design group, they used sleep and idle modes because it allowed them to do power conservation. So they were using something that was solar powered, and it sat in your lawn, and it was an alarm system if someone crossed a threshold. So that was something that they wanted to, they're only using this little solar panel. They want to make sure they use energy only when they need it because it was doing wireless transmissions which were high energy usage. And so their group used idle mode quite a bit. But they still needed to use certain things outside or while they were in idle mode. ADC was one of them. That's how they sampled to see if someone crossed the threshold. So they needed to keep that on. But everything else they would turn off. So the next bit is 8012B. This says, do you want to do 10-bit or 12-bit operation mode? So that talks about how many bits of resolution do you want. So we talked about earlier having 0 to 10, right? So 10 bits is what, 1000 or something? Was it 1024? 1024 values that you can have between each voltage. So you take your voltage that you're referencing, 3.3 volts, divide that by 1024. Let's go ahead and do that actually. So we got the calculator. We've got 3.3 3.3 volts divided by 1024. So our resolution, if we use 10-bit operation, is 3.2 millivolts. That means every time you change 3.2 millivolts, we can detect that. We can see there's been a change. If we use 12-bit operation, we have 4096. So you take 3.3 divided by 4096, and now you have 800 microvolts of resolution. So that's quite precise. You know, when you kind of think about it, this little $2 chip, 18 pins, is able to detect 800 microvolt difference with a default reference voltage. So we're going to go ahead and use 12-bit because, hey, why not? Because we have one channel. 12-bit is only available when you use one channel operation because it uses some of the resources that would be otherwise used for the other channels to operate. So I shouldn't say that. I should say the other channels don't have they can't access the resources that are used for 12-bit because they just can't fit that much on the chip. So when you use 4-channel operation, which the Micromouse actually uses, it can only use 10-bit resolution. But today we'll do 12. So we'll make sure 8012B is set. Okay. Next thing says data output format. Data output format says, so we'll make sure we look at the 12-bit operation instead of 10-bit because we're using 12. We can either make this a signed integer or make it a regular integer. So a signed integer might be useful if you were doing negative voltages. So like a lot of like op amps and things have like negative voltage rails, right? And then, so you'll swing between, you know, say +3, -3. But for our use, since we're only going between 0 and 3.3 volts, we'll only want an integer. So we'll make sure that's set to 0. So form needs to be set to 0. The next thing says sample clock source select bits. This one's about this says internal counter ends sampling and starts conversion. This is auto conversion. What this says is as soon as you're done sampling a value, we'll start converting that value to a digital number. However, you don't have to do that. You can also say something like clearing the sample bit ends sampling and starts conversion. So that would be better on a polling procedure, right? Where you would have to actually clear that sample bit. So if we come back up, you see this samp. We haven't gotten to it because it's down a little lower, but this samp is one of those that the hardware looks at. It's also a read-write. So we could clear that sample bit and it'll say, oh, he said stop sampling. I'm going to stop sampling. Now I'll go ahead and start converting. The other stuff you can do is active transition on interrupt 0 pin, ends sampling and starts conversion, or GP timer 3 compares ends sampling and starts conversion. These are a little more complicated processes. I don't know of examples to give you, but it's using other things to tell you to stop the sampling and start the conversion. But for us, we just have the internal counter go and say, okay, as soon as that internal counter ends, let's stop, let's start converting. So SSRC, we want, this is 111, that's 7. So we want to make sure SSRC is set to 7. Oops. Alright, SimSam, simultaneous sample select bit. What this is for is if we had 4-channel sampling, we may want to sample all those channels at the exact same time. So that might be really important because if you want to check like 4 values and change what you do based on each of those values, you would want them all to be checked at the same time. You don't want them to be checked in order or in different times because they could have, you know, different reactions. So for instance, if you had something fast like I don't know, let's say you're sampling all your LEDs. This is actually a perfect example. You're sampling all your IR LEDs on the Micromouse. And you guys have 4, right? So there's 4 sampling LEDs. There's 2 diagonal and 2 in the front. And you want to make a decision on where you're going to turn or where the Micromouse is going to go. And you don't want those values to be different, right? You don't want to look at what are these values right now and then what are my front values in 2 seconds, right? You want to see everything at the same moment. What are all these values right now? And that way you're looking at things in a more instantaneous fashion. So for us, it doesn't matter what we put here because we have 8012B equals to 1. So it says when 8012B is equal to 1, this one is unimplemented. Read as 0, so it doesn't do anything. It doesn't matter what we do to that. So we'll not even set it because it's unimplemented. So the next one is auto sample start bit. So this one says sampling begins immediately after the last conversion. So if we set this bit, if we set this bit, the sampling will begin as soon as it converts a value. So it says as soon as I figure out what the digital value is that represents this analog voltage, I'm going to start sampling again. Or you can tell it, don't sample again until I flat out tell you to. So that one's another one that's really good for conserving energy and resources, because you could say 0. That way you could say, you know, if I want to do all this math with this value, this analog value, I don't want you going and finding another value and then interrupting again before I'm even done with the math. I want to wait till I'm done with the math, and then I'll come back and ask you to look for it again. So, you know, we'll go ahead and do the, actually, now that I think about it, we could maybe just go ahead and, we could do that. Well, let's just go ahead and do the auto conversions, because this is easier. So we'll say ASAM is equal to 1. We could, in our case right now, we could do sample only when we tell you to, because we're going to do a little bit of math with it, but not a lot. The next one is a sample enable bit. That's exactly the bit we would set to tell it to start sampling. But since we're not setting it, we can also just look at it. When the sample and hold amplifiers are sampling, the sample bit gets set. So you can tell it to start sampling, and it'll stay set until they finish. When it's 0, they're holding the value. So when the sample, basically it comes back to, if we look back up at this picture, when this is closed, SAMP is set. When it's open, it's not. So the value is being held on the capacitor, right? So this SAMP literally just corresponds to, where is this latch? Is it closed or open? So it's that. The done status bit, that's again, you know, we talked about earlier, if you didn't have an interrupt, you could sit there and pull the done bit and see if it's done. So now let's go to the next control register. So that we just did a con 1. Let's go ahead and back down here. Let's say AD1 con 2. That's our next register we're working on. Alright, so AD1 con 2. First thing it has here is converter voltage reference configuration bits. So this says, what do you want to use as a reference point for your conversions? For us, we're just going to use the microcontroller's default analog VDD and VSS. That's something to think about too. So you guys are used to VDD and VSS, right? You always see that on your microcontroller. And actually this one only has a VDD and a VSS. But on Micromouse's chip, there are VDD and VSSs, and there are a VDD and a VSSs. That's a separate VDD and VSS dedicated to analog stuff. So you would want to put your analog stuff on a separate grounding plane and a separate power source, because the reason is, why do you do that? Because digital side is extremely noisy. It's super, super noisy because you have clocks going like crazy and you have constant rail-to-rail ringing in crap. Digital is messy. It's really noisy. They use all kinds of things like Schmitt triggers and stuff. You guys remember Schmitt triggers from the 7400s, right? Schmitt triggers are used to kind of clean that up, and they do a great job of it. So digitally speaking, we don't care that there's a lot of noise on it. We're still able to get all the info we want out of it very accurately. But on the analog side, when we talk about analog, we're talking about continuous systems, not discrete systems, right? We're talking about things that have infinitesimally different values. So an infinitesimal amount of noise can change things, right? So we want to try to limit that noise to as low as possible. So we do that by putting it on its own ground plane, its own power plane, but then we also have its own reference points because of that. So we can use those reference points by default by leaving this VCFG as equal to 0, which we will. Let's go ahead and do that. But the other options are, we could use an external reference. We could use an external positive reference, which would be useful in this case we talked about earlier. We want to share the same ground. We don't care. 0 volts is 0 volts, right? We don't care about the ground changing. But maybe we want to change our positive reference. We want to look at 1 volt. We don't want to look at 3.3 because we lost a lot of accuracy. But you could also change the negative reference. And so that would be useful if you were, say, doing between 1 and 2 volts. Let's say your minimum voltage you ever see is 1 volt. The maximum voltage you ever see is 2 volts. You want to get maximum resolution, you put it between 1 and 2. You don't put it between 0 and 2, or 0 and 3.3, or 1 and 3.3. So you have all those different options. You can see this chip is extremely versatile. It can do anything you want in most cases. So we're going to go ahead and make sure we made sure that was set to 0. Next bit here, scan input selections for CH0+ during sample A bit. So one of the things you can do with channel 0 is you can scan as many analog inputs as you want. It will run through all your analog pins and sample them and put them in respective buffers. So you have 16 buffer channels. So it can go through and sample, I think I said there were 6 on here, something like that, 6 analog pins. You could go through and sample all the analog pins and set them all to channel 0, so they could all have 12-bit operation as well. And you could store those all in the buffer on their respective buffers. So AN0 would be buffer 0, AN1 would be buffer 1, so on and so forth. So you could scan through all of them. The downside, it's not simultaneous sampling. It's going to cycle through everything, and it takes it some time. So it goes and samples, converts, then it goes to the next one, samples, converts. It's probably really fast from anything that we would be doing, but in a Micromouse, it's not maybe fast enough. So we're not going to use that though because we just have one input. So we look back at the bit CSCNA, it defaults to 0, so we don't have to touch it. CHPS, select channels, utilize bits. This one just says which channels do you want to convert. Well, we only want to convert channel 0 because that's the only one we're doing. But if we were using 4-channel sampling, we'd want to use all 4 channels. So again, we want to see CHPS. That defaults to 0. We'll leave that alone. BFS, buffer fill status bit. This bit alternates the whole time that it's filling up buffers. So that you can, if you wanted to check information super fast, then you would say, hey, look at this buffer bit. If the ADC is filling the second half, let's go look at the first half. If it's filling the first half of the buffer, let's go look at the second half of the buffer. So it'll tell you what part of the buffer it's in. So you could access those values even faster if you wanted to. Or if you were doing some other kind of, you want to play. A lot of programming is playing little gimmicks, little tricks to improve things and make things faster and stuff. So maybe you want to utilize that for whatever reason. The next thing is sample convert sequences per interrupt selection bit. So this one is another one of those kind of timing things where you just kind of want to see, or maybe you want to do averaging. This one says how many times do we need to sample that channel before we interrupt, before we actually say, hey, CPU, time to deal with this information. So we can sample it up to 16 times, and it'll store it in respective buffers again. So if we sample just once, it's going to be in buffer 0. If we sample 2 times, it'll be in buffer 0 and buffer 1. If we sample 3 times, buffer 0, 1, 2, or 0, 1, and 2. So all the way up to the 15th buffer place, which is the 16th sample. So we can do 16 samples, say, then interrupt and say average those samples, or look at the most recent one, or look at one in the middle. Whatever you want to do, you have all kinds of playroom there. Now for us, let's just go ahead and interrupt every time we do a sample because we don't really care. So SMPI should be equal to 0. The next one is buffer fill mode select. So this one says starts filling the first half of the buffer on the first interrupt and second half of the buffer on the next interrupt. Or 0 says always starts filling the buffer from the beginning. So since we're doing 1, we don't give a crap. We only use 1 registered buffer, so we're just going to leave it whatever its default is, which is supposed to be 0, yeah. And then the last thing is ALTS, alternate input sample mode select bit. So this is that one I was talking about, the alternating input. So you can alternate sample. So you have the A bits and the B ones. So you can do channel 0 during A sampling and channel 0 during B sampling. So you could alternate your pins on which ones you're checking. Again, it's kind of like that scan mode, except for if you had 4 channel, you can do 4 here at the same time and then 4 of another one at the same time. So it really just lets you double up on your ADC module. Now, a lot of these bigger chips, like the Micromouse chip, actually has two ADC modules.
Yeah.
So there's two modules you can configure in there, two totally separate ones that can access both. I think they can both access all the pins. So there's that as well. So you have a lot of options there. You can either use a separate module to do 4 different channels. So if you want to sample 8 channels, let's say, module 1 samples these 4, module 2 samples these 4, or you can say module 1 samples these 4, then these 4, then these 4, then these 4, whatever. You can do whichever way you want. It just allows you to play around. So the default on that also 0. We just want to use the A bits because we're just going to sample one thing. All right, so that's done for that register. We've got another register, AD1Con3. All right, first thing here, ADRC, the conversion clock source select bit. So earlier we talked about how you could use the internal clock or you could use a clock from the system. Well, let's just use the internal clock because why complicate things? So ADRC is equal to 1. Let's use that 4 megahertz clock. It's super fast, and I don't really see any other reason not to use it. The next thing says the auto sample time bits. So this, and it's always, whenever you see these numbers, it's always good to scroll down and see what the heck are they trying to. They're trying to tell you, hey, look down here. There's some more stuff you might should know. So we come down here. It says these bits are used only if the SSRC bits are equal to 7, which if we go back, our SSRC is 7, so we do need to use this. What does this say? Auto sample time bits. So this says how long are we going to sample? This is how long are we going to leave that latch closed. It is a number that is multiplied by our TAD. And our TAD, if we scroll back up, TAD is our analog to digital period. In this case, it's 250 nanoseconds because we use the inside of the chip, right? Or the inside of the ADC, the internal one. So we can say this is going to be, 250 nanoseconds, or 2 would be 500 nanoseconds, or, 4 would be 1 millisecond. So, you know what? Let's do 4. Let's do 1 millisecond. Why not? So that was called what again? SAMC. Next one says ADC. Why does the scroll stop working every once in a while? It's driving me nuts. It's just, nope, not going to scroll. It's Mavericks. Stupid. Okay. Sorry. The ADCS, ADC conversion clock select bits. So this one says, how long do you want to spend converting? Or sorry, I shouldn't say how long do you want to spend converting. The conversion clock, the clock you're going to use to go through the conversion process, what do you want it to be? Do you want it to be like a number that's higher than your analog to digital sampling clock, or do you, so you want it? It's kind of how long do you want it to take in some sense, but it's saying what kind of clock do you want me to use. So for us, let's just go ahead and use 1 because or 0 actually, because it'll just multiply our TAD will be just. I'm sorry, take that back. This is wrong thing. This is not used if you're using the ADRC. So this is multiplied by your system clock. So if you weren't using the 4 megahertz internal RC, then it would say multiply your system clock by this number, and that gives us our new analog to digital clock. So that's actually, sorry, take back what I said at first. I thought it was something else. All right, so we'll leave that alone. It's unimplemented since we're not using that. The next thing, so we're done with that register. The next register here is about the ADC channel 1, 2, and 3. We're not using those. We're only using channel 0. So if we keep going down, here's AD1CHS0. This is input channel 0 select register. So we want that one. We're going to say AD1CHS0, right? Yeah. All right, so this one says, first thing, channel 0 negative input bit for sample B. We're not using sample B. We talked about earlier the alternating samples, sample A, sample B. We're not using B. So scroll down a little more. Channel 0 negative input for sample A bit. Well, we can either use AN1 for the negative input, or we can use channel 0 negative input is VREF. We want to use VREF. We just want it to be with respect to ground, right? So this is for the sampling. So don't get that confused with the conversion. Earlier we said, okay, what are our ADC conversion references? This is for what point do you want to sample? So this is kind of interesting because maybe we have a circuit like this. Let's say we have some voltage source that could be 40 volts, right? And we have this voltage drop here and a voltage drop here. Well, let's say that this one is going to take up 39 of our volts, right? And then we want to sample what is the voltage here, because let's say this one ranges from, from 1 volt to maybe it goes over to, I don't know, 3 volts, right? So some range in there. So, and this is, whatever that difference is. So this can go from 39 to 37. So the microcontroller can't handle 40 volts. We don't want to say, what is this with respect to ground? Because this with respect to ground is 40 freaking volts. That's going to blow our microcontroller. And it's not even going to tell us a voltage change because we're going to be including this, right? So we'll say, oh, okay, well then our AN0 negative sampling, or I guess I should say CH0 negative sampling is going to be here, and our CH0 positive sampling will be here. And now we can detect the difference in voltage across that resistor. And we don't blow the chip, for that matter. So you want to make sure you have the right reference point for that sampling. So in our case, though, we're going to reference to ground. So we'll leave that to 0. What is that? CHONA, or CH0NA, 0. That will really mess you up. I think me and Matt sat there one night for like 20 minutes before we figured out.
Which one?
O and 0.
Oh, yeah.
So, yeah. The next one says the channel 0 positive input for sample A. So the positive input is obvious, just where do we want to get the positive input voltage. So we're going to use AN0 we talked about earlier on pin 2. So we're just going to set CH0SA equals. Wait, is it 0? Maybe it's, oh, I forgot my underscore. All right. Next thing for the register is ADC1 input scan select. That goes back to that scanning thing. So we're actually done. We don't need to do anything for that register. We're done with ADC configuration, but we never told it how are we going to interrupt and what to do with the interrupt. So let's go ahead and stay in this config as ADC, but let's kind of break off to the side and say, let's open another register name, and we're going to call this the interrupt stuff. All right. So now, if we come back up, we go to the interrupt controller, 59. Alright, so the interrupt controller. What's going on here? Well, there's this like interrupt vector table, which I'm not even going to act like I know a ton about. I don't know this very well. But there's this whole thing going on in the background where it goes and it looks for certain things to happen. And when it happens, it interrupts. It tells, hey, the CPU, it tells the CPU, whatever you're doing, you need to come over here and look at me. I have something going on. And it deals with that in what's called an interrupt service routine. An interrupt service routine is basically a function, but you can't pass anything in and you can't pass anything back because it gets called wherever and it returns wherever it came from. So it doesn't ever, when you have because when you have a function, you always say, here's my function, here's the values I want to pass you, right? You give you pass downs. And it goes down there and it says, okay, he gave us this, and so we're going to do this with that, and then we'll give him back a number. Well, interrupt service routines are, you still go to that section of the code, but you don't get anything because you don't know. I mean, you could be doing it while you're doing 1 + 1, or you could be doing it while you're calculating the 4,000th digit of pi. It doesn't know what it's going to get, so it doesn't try to get anything. And then same thing for going back. It can't feed back a value. So never think, always think that, I can't return anything and I can't have anything come in. So this is something you got to think about. You got to do things on a global scale. If you're going to be set, usually when you go into these interrupt service routines, the other thing is you don't want to screw up a lot of timing. you're in this routine that gets called who knows how often. You want to get in and get out. Change maybe one thing just to let you know that something happened. So let's look at this. This talks about addressing for the interrupt vectors. They have addresses for each type of interruption that you can have. You can have interruptions for all kinds of stuff, from input captures to UART to timer interrupts. But we want to do an ADC interrupt. So let's just get down here into the registers. The first thing we want to talk about, this says CPU interrupt priority. We're not using a CPU interrupt. I don't even know why they put this in here. I'm not a pro when it comes to this interrupt stuff. I'm not 100% on all of this. So I don't even know why it's here. These priorities, so like if you had the CPU at a priority level of 7, that means that user interrupts are disabled. That means, because 7 is the highest priority an interrupt can have. So if you're saying, I guess if you're saying the CPU has the highest priority, that means that nothing else can ever override it. So it can never be called out of what it's doing. So I guess this is like some default thing, but I don't know why you would ever want anything higher than 1, to be honest, because then why are you even including these other interrupts? So that's why I'm saying I'm not a pro at this, because I don't remember, or I don't know this. This goes into a little bit more of that CPU stuff, but here's what we're interested in. So IntCon1 is our first control register. This is one of the first things we want to make sure doesn't happen. This is nesting disable bit. We don't want the interrupts to nest. Nesting means that you can get into another interrupt from within an interrupt. That can really screw you over. So we're going to make sure that's turned off so that whenever we're in an interrupt, we're going to finish that interrupt before we get called anywhere else. It's not going to happen on our chip and on our project right now, what we're doing. It's just not going to happen, but it can happen, I guess, in other things, and I don't even know how you want to deal with it in the future, but we're going to make sure that's off just because I don't want to get stuck in some weird forever
Something I
loop.
want that is you have something that's absolutely critical, like you need to write to an SD card or something at exact increments, and you don't want to be in another interrupt whenever you need to be writing to the SD card.
Yeah. So, I mean, well, then we do.
So if there's one...
But see, the nesting has to do with the same priority level, doesn't it?
I believe so.
So the thing is that we always set priorities, and so the priorities would kick
But
you
if you
out.
turn that off when you're in an interrupt, you can't go into another interrupt.
So the other thing is you want to hopefully make sure that you're not in an interrupt for a long time. I guess it would be really something you want to think about when you're in a long interrupt.
Yeah.
I don't know. Anyways. So there's a lot of things you can call an interrupt for. Arithmetic errors, addressing errors, all kinds of stuff. We're not really interested in those right now. We're going to skip down to the next register. We have the interrupt flag status register. So this one is important, 81IF. This is our interrupt flag. If that flag is set, the interrupt service routine will be called. If it doesn't get cleared, the interrupt service routine will continue to be called. So you got to make sure when we're going to make an interrupt service routine in a minute, the first thing you always do in interrupt service routines is clear the flag. Because if you don't clear the flag, you will stay in that interrupt service routine. Every time you finish it, it will be called straight back into it. That flag is the signifier, the bit that says, hey, deal with this. So the first thing we want to make sure we do here, AD1IF is equal to 0. Make sure that flag is cleared. So then we scroll back down. Obviously, this has it for everything. You know, UART transmission, receiving, SPI, timers, output comparators, everything. So let's just keep going down now. We have more flags. Forget those. We're only concerned with this one. The next thing says interrupt enable control register, AD1IE. That one says, hey, when you hear or when you see the flag for the AD1, for analog to digital converter 1, deal with it. Let it call a global interrupt. There's also a global interrupt bit which we do not have to set. It's defaulted on, which basically says listen to the interrupts. This one says listen to the ADC. Otherwise, if you don't set this, that flag can get set, and the microcontroller goes, I don't care about that. I'm not concerned with that. So it won't even listen to it. But yeah, that is. Oh, the only other thing we need to do is the interrupt priority control. And so we'll come in here and we'll find the interrupt priority for the AD1. AD1 IP. And so obviously, like I said before, 7 is the highest. 0 means disabled. So we'll just put a priority of 2. Okay. So now we've set up the interrupt for this module. We've set up the module itself. We've set up the pins around it. And the only other thing remaining now is to do the interrupt service routine. So let's put a little space there. This will actually finally turn it on once we're done, right? So we'll put that down up here. Let's put it right up here. Now, there is a naming convention for these interrupt service routines. I can't remember where I found it, and I'll let you guys know as soon as I find it again, because it's driving me nuts. I think it's in the chip, but I can't quite remember. Those interrupt service routines, they're not in the datasheet because it's based on the compiler you're using. So we're using XC16, right? So XC16 calls the shots on these interrupt service routines, how you call them. Me and Matt found it one day. It took forever to find it, but there is a specific convention, and they have specific names for everything. So I'm just going to copy it from my code to show you it and to use it. Well, what am I looking at there? Oh, okay. So this is it. You've got this void attribute underscore underscore attribute underscore underscore open parentheses underscore underscore interrupt underscore underscore comma underscore underscore no underscore auto underscore PSV underscore underscore. So this is, and then it has a name for the ADC one. So that was something else, by the way, Matt. That chip you were using was AD1, remember?
Yeah.
My chip is ADC1. So sometimes they're called AD1, sometimes they're called ADC1.
They're probably called other things too.
And yeah, there's probably other names for other things. It's really annoying because this is one of the toughest things about the microcontroller is finding the naming convention. It's not actually using it, it's just finding the name of it and using and setting it up properly. But this is what you have to put there for the function name for it to treat it as an interrupt service routine. So now, first thing I said, when we get in an interrupt service routine, 81 interrupt flag equals 0. Make sure, off the bat, clear that flag, or else we'll get stuck in there forever. And what we want to do is we want to go grab the value from the buffer. And if you look in the data sheet, you'll find out that the buffer is called, let's go ahead and come up here actually and say, beforehand, let's declare a global variable, let's call it a float. No, let's call it an int. Int of, let's just call it temp ADC. And what we're going to do is come in here, we're going to say temp ADC is equal to ADC1 buff 0. ADC1 buff 0 is the 0 buffer for the ADC1 peripheral. And that's all we want to do in here. And then we're going to get out. So that flag is cleared, and we move this value into here, right? So that's only a couple instruction cycles. We just want to make this as fast as flippin' possible. For other things, you might want to come in and just set a bit. I equals 1, I equals 0, I equals not I. You know, just flip that bit every time you go in. Something like that. Something really simple. You're either setting a bit or moving a value, and that's it. Get out. We'll do the math later. So, while we're here, let's make sure we config pins. We'll config ADC. That's what we call them, right? Yeah. Alright. So now, what we'll do is, inside of here, inside this main function, let's define a local variable. We'll call that a float, and we'll call it the AVAL, the analog value. We'll declare it as 0.0, just to start it off. And what we'll do is, we want an infinite loop, because that's how a microcontroller works. We always want it infinitely looping, and we'll interrupt whenever we need to deal with something. So in this infinite loop, we're going to say AVAL is equal to temp ADC. So just to be safe, so that that doesn't create an issue, let's declare initialize ADC temp ADC to 0. We want temp ADC times 3.3. divided by 4096. And what that does is it turns it into a voltage. We've taken those 4,096 values that it could be, and we divide that from 3.3, so that's each of the voltages it could be, and we multiplied it by the number it gave us back. So now we've taken that ADC value that we got, we've turned it into a voltage. And then we're going to say if the A val is greater than 3, then we said we have high LED, and we'll set that. If medium LED, we'll set that. If LLED, we'll set that. So if it's greater than 3 volts, we're going to set all 3 LEDs. Else if A val is greater than 2, so if it's greater than 2 volts, so if it's not greater than 3 but it is greater than 2, then we're going to say HLED is equal to 0, MLED is equal to 1, LLED is equal to 1. So we'll turn on the medium and the low light, but we'll keep the high light off. And then else if A val is greater than 1 volt, and let's just copy this. We'll set them all except for the medium LED, or sorry, set only the LED. And then finally, if nothing is, if it's not higher than 1 volt, then we'll just clear them all, make sure they're all off, right? And that should be it. So now we've written a program that should read analog 0 on pin 2 into channel 0. It should look at it, convert it to analog value or digital value, and then compare that value to 3, 2, and 1 and set these lights accordingly. So let's try to program it. And let me make sure. Oops. PIC. Hopefully we don't get any errors. Cool. Alright, and it's working. So, as I have a high voltage, all 3 are on. Turn the voltage down, it's above 2. Turn the voltage down, it's above 1. Turn the voltage down, it's under 1. And there we go. So now we're analog sampling and reacting accordingly. So you can apply that to other things. You know, some of the things that you guys are going to be doing with that is like pulse width modulation, or you might be doing, I don't know, just stochastic responses, like stuff like turn left and go through a routine. But I set it up on digital pins because obviously it gives you guys an idea how to use digital pins, number 1, but number 2, they're super easy, right? But yeah, so that's about it. Does anyone have any questions? Huh? Oh yeah, no. This is one of those things that you can't learn just by listening to me. You guys are really going to need to go home and try this on your own now. And it's one of those things that it takes a lot of trial and error. And it does help a lot to obviously talk it out with teammates and stuff like that. So please feel free to come hit any of us up that know about this, and we can help you. But it's one of those things that takes a long time. It's not something that's just like easy. But the first time you set up a peripheral, you really start to carry those skills over, and you'll set up the next peripheral faster and faster and faster, and then it becomes very easy. So you also got to learn how to navigate that data sheet. Navigating the data sheet's half the battle too. But yeah.
Can you say again about how you calculate the clock with the variable N1, N2, and N?
Oh yeah. So he's asking about the oscillator configuration. So if we go back to the oscillator configuration, So oscillator configuration says, if we scroll down here, it says that F oscillator, which is our clock of the chip, not necessarily the instructions of the chip, but the clock, is equal to the F in, which is the default clock on our RC oscillator. Now we could use an external clock, right? We could use a crystal oscillator, or we could use, something like that, a ceramic oscillator, something like that. But we configured our chip to be the FRC, the internal oscillator. That has a default value of 7.37 megahertz. So we take that 7.37 megahertz, and it says you now multiply by 1 and then divide by N1 and N2. But not only that, you also have to meet all the requirements that are shown in this block diagram. And in this block diagram it says for N1, whenever you take your internal oscillator default frequency 7.37, you take N1 and you divide off from there, and now it has to be between 0.8 and 8. And then once you get through there, it'll also multiply that number by M and feed through the voltage control oscillator, and then it has to be between 100 and 200 megahertz. And then finally with the PLL post, you divide again by 2, 4, or 8, and it has to be between 12.5 and 80.
So I don't understand when you set the value of variable N1 equal to, and then in the Excel file that you created, and I saw that you get the value that is 2.456.
You want to stay and play?
Huh?
You want to stay and play?
I got a group meeting.
So, sorry.
In the Excel file.
Oh, the Excel file. Okay.
When you set the values of N1 equal 3, how can you get 2.4560?
Because it's 7.37 divided by 3.
Oh.
Yeah. So 7.37 divided by 3, you get 2.45, right? And so that's this right here. And then you take this number, 2.45. Now you multiply by 65. So now we take that, multiply by 65. That gives us 159.68.
So the requirement is the in internal frequencies multiplied by the 3 variables must be in the range that you give right here.
Yeah.
And then we apply the formula to get the F of oscillator, and then we divide by 2, we get F of C1.
Well, yeah, and so that's kind of like an implied divide by 2. It's not something that actually you're going in and dividing by 2. It's something that just realize that that's FCY is your cycles, your instruction cycle frequency. So that's how many instructions per second you can do. So in this case, it's 40 million instructions. So there's 40 megahertz is 40 million instructions per second you can do. And one instruction cycle is like one move, right? Move from file to working register. That's one instruction cycle. So that's 2 clock cycles. And that's just because the D flip-flops inside. It works like the inside of it is just D flip-flops everywhere. And so it takes 2 cycles to make one value move.
Okay. And so the internal frequency that you have said that we had a period 250 nanoseconds. So that's one we just used to calculate how long you used to take the same sample. Right?
It does that and the conversion. So that's actually just defining what does the ADC module, the peripheral, what does that peripheral use as a clock? Well, it has its own internal RC clock, so that if you wanted to just use its own clock and not have to worry about what the system clock is doing, you can. And so that's what we did because it makes it easier. But you don't have to. You can use the system clock. You can use some variation of the system clock. You know, you can say, I want this to be, I literally want this to be 10 times slower than the system clock. And you can do that. You choose the value 10, or actually it'll be 9, and it makes it 10 times TCY, which is TCY is 1 over FCY, and 1 over FCY, in this case, is 250 nanoseconds. So by making it 4 megahertz, it was...
So in this code, you just use FCY to calculate how fast the microprocessor will read one instruction, right?
How fast? What? Sorry.
How fast the chip PIC24 read one cycle, right?
Yeah, that's what you're setting there. Yes. Yeah. Does that make sense?
Yeah.
Cool. Does anyone else have any questions? Okay. Simon, how do I stop this?
What do you know? Go back to that little window. There we go.
It's gone.
Oh. You sure?
Stop screen.